Hello, everyone. Welcome back to day 2 at Heapcon. Our first speaker for today is Nemanja Mitić. Nemanja is a software engineer at Rivian with over 20 years of experience convincing computers to cooperate. He also has a decade specializing in AWS architecture. Nemanja now works on Rivian's electric vehicle platform and will show us how Rivian creates dynamic digital twins for every vehicle, tracking millions of events from factory assembly to final delivery. Please give a warm welcome from Nemanja.
Thank you so much for a wonderful introduction. Sorry for my voice. My voice decided like 2 days ago to go on vacation, so sorry for that. I'm probably mutating into something, we'll see. Anyways, as the slide says, my name is Nemanja. Thank you all for attending. I'm from a company that's called Rivian, that lies somewhere in one of the plethora of categories of the industries that the company resides in. In this case, it's the automotive industry. But that's not the end of it. So, as you know, we are not manufacturing cars in Serbia. We have a very big research and development center. So, I guess that we like to say that Rivian is, even though it's creating electric cars, is a software company, especially in Serbia, where our research and development center in Serbia almost counts more than 400 and something heads. And in Serbia, it's not just one branch, because if you want to create a car, especially an electric car, which is literally computer on wheels, multiple computers on wheels, you have to have different teams developing different pieces of that car, software-wise. Of course, the factory employs the biggest amount of people, but we are a software-driven company, and we like to build stuff in-house. So a lot of that software has been built in-house from, as you will see, from the point when the assembly line starts and the car gets married with the chassis, the motors get married with the chassis, all the way to shipping the car to the customer or customers who bought it, because we also sell fleets of vehicles to our business customers. Like, for example, our biggest customer is Amazon. You know that besides cars, we also make those electric delivery vans, or EDVs, how we call them. You might have also seen them if you were in Germany, like in the past couple of years. We also started shipping those to Germany to be used by Amazon. So, today, we're going to try to go through. So you're probably not going to learn anything new, but there is something for everyone here. So I'm going to show slightly how the manufacturing process works, because building a car is anything but easy, anything but organized. It's like a coordinated chaos that needs to come together, and the customer gets their vehicle back in the end. That's working, of course. We are going to go through a couple of pillars, and these are literally groups of slides in the presentation. So we are going to see how we manufacture cars in the factory, and how one small signal, how we call it, or event, call it whatever, because in today's world, event-driven architectures are a thing, right? So we no longer build monoliths, and most of us no longer use bare metal for hosting our apps. We usually, cloud native and event-driven architectures are a thing now. So why not? If it works, it works. And let's see how we utilize it in Rivian. So we are going to start from like some 3 pillars throughout and one event's lifecycle. And we're just going to pick one single scenario out of like a million scenarios there is, because people developing cars, of course, and developing software for that cars, there are a million scenarios to choose from. I just picked one small scenario to just intrigue your your brain. And if you'd like to find out more, we literally have our engineers down there at the booth, and feel free to stop by and ask us any question that you might have. So we're going to go through 3 pillars. One is how machines assembling cars in the factory are being configured by software. Then we are going to move to another pillar, which is collect, which is when the manufacturing is not just producing a car, it's also shipping a vehicle to a customer. Then we are going to move to a second pillar, which is now we collect information. which is that signal needs to be created somewhere. Now we investigate how we configured our machines at the manufacturing process. And then we analyze that in the cloud and in third-party software that we use, third-party services that we use, sorry. One of them being Databricks, of course. We're not just using cloud, of course. So, without further ado, let's continue to the journey of one single event, how it travels back all the way from manufacturing, then to collecting the signals, and then learning how we can improve both of those, even the cars that we already shipped, and then bringing that back to the factory so that we have like full end-to-end life cycle of one single event and how it impacts the wider audience, not just the factory, not just the customer, but also us as engineers. As I said, it's a mess. It's an well-organized mess. So, out of the factory employs, as I said, the biggest amount of people because you simply cannot automate everything. So, in our factory over in Normal, Illinois, we have press shops, body shops, paint shops, assembly lines, all like millions of different machines that need to be configured either via how manufacturer dictates the configuration that comes with a particular machine, and then a worker needs to be trained how to use it. Then the end product, hopefully if everything works well, of course, is a drivable vehicle that we deliver to our customers. So, of course, all of these machines, as I said, need to be configured somehow and somewhere. That all happens partially from that. Sorry for this, we lost the slides. I still have them here, though. Shall I just disconnect and reconnect? Okay. Okay. So where were we? From, if you want to configure a particular machine in a factory, you have to be very careful because creating problems on one side of the factory just cascades down to the whole assembly line that we have. And of course, making a mistake in any of the machine's configuration creates huge amounts of problems downstream. As I said, we're going to pick one single scenario out of everything that happens in the factory. It's millions of processes to get the car assembled and ready to be shipped by. You're also going to see how we ship cars too in the next slides. So the scenario I want to go through with you is, let's think of a machine that kind of just tightens a bolt, okay? The machine that tightens, it's the arm, not the chassis thingy down there. The machine that tightens the bolt is, of course, you get a manual from manufacturer when you order the car, when you order the machine. Then it comes with some software. It might be that black box that we need to communicate to. And every manufacturer has their own ways of course, communicating with whatever outside it is. And we want to be able to communicate with that machine, to be able to configure it, to create kind of the full cycle so that it can manufacture the part, the car can be put in a vehicle, the customer can drive a car. We can listen to how the chassis behaves, maybe tightening a bolt slightly better or differently, or using different lubrication or configuring machine differently. This is just one of the scenarios, though, as I said. Can maybe introduce less rattle, maybe in a particular part of a vehicle, maybe can increase the lifespan of a vehicle, and that's what we are trying to do here. So every of machines in the factory comes with its own black box, but a black box as how it communicates with the machine, but it has an API, of course, and we strive to do that. So why do we need an API? So as I said, if we go back, we want to be able to configure the machine remotely. We want to be able to then listen to how that part behaves in the car, and then we want to learn out of it, and then we want to reconfigure the machine back, maybe to extend the lifespan of that part in the future generations of a car, or even replace it if the machine is not working properly. In this particular scenario, so The UI you see on the right side with all the blurred lines, of course, because it was the screenshot of one of our production lines, and there's customer data here too. It controls how this machine in particular tightens this bolt and whether it's ready or not. And this software, this tool has been built internally by our software engineers and is installed inside of the factory and can be configured remotely. And then that software talks with that black box, in the end controlling how the readiness state of tightening a particular bolt or 5 bolts, or doesn't matter how many. The other scenario would be, for example, you know that every car, as I said, it's literally computers on wheels, has millions of ECUs, how we call them, electronic compute unit. Those are literally small computers. And in our R1 generations, we kind of had a huge revamp of how our harnessing looks like and how many ECUs are we using. So we went from 20 plus to 10 plus ECUs, like within a year and a half of research and development. So all of this process made sense because now we are simplifying the process. We need less computers now than we needed like 3 years ago to manufacture our R1 generations. Okay, our R1 model cars. The same thing happens with EDVs. So it's probably going to come back online. So the same thing comes with our EDVs. So those are the delivery vans that are being used by Amazon. So we sell a whole fleet to Amazon. A fleet of vehicles, of course, Amazon doesn't buy 1 or 2, it buys thousands of vehicles. So the same thing applies. We have to learn, we have to figure out whether the configuration of all the machines in the factory, they're properly configured, and whether we can improve a process. So as I said, we went from this process actually lived through one big revamp. As I said, we went from 27, 8 ECUs in a vehicle down to 13, 14 ECUs that are now living in a particular vehicle. I'm talking about R1 generations. EDVs are a completely different story as to how many ECUs they have in them. So this is still the manufacturing process, but this is not where the manufacturing process ends. You cannot just build a car and consider the manufacturing process done. In my opinion, in our opinion, sorry, the manufacturing process is done when you actually deliver the customer when you deliver the vehicle to a customer, which you're going to see in the next slide, how it all looks. So this is how our outbound yard looks in Normal, Illinois. So the factory is on the left. The factory, this has a pointer, but it's not working. So this is the factory, this small white box, and then all the way to the left. That's the factory. And this is everything that happens post-production, so post-assembly line. And we built software for this too, because we have to optimize this. As you can see, there's a huge rail yard here with rail cars, etc., because this is the most efficient way to ship all throughout all throughout the US. Because when you want to ship a particular vehicle or EDVs, look how many EDVs we have. All these blue dots are EDVs, and all these cars in there. The yard goes beyond even there on the back. And then we have a charging yard because the manufacturing is not done yet. Because, for example, one example of manufacturing is not done yet, and why we have to have software for this too, not just the factory, is maybe the customer ordered that foil that protects the paint. That happens post-production in this white building where the vehicle gets wrapped in a protective film. And there are multiple more scenarios, of course, than this. So, as I said, the manufacturing is not done yet. We built a software for this, which we call Yard Management System. And this software controls that we ship the right configuration of a vehicle, because, of course, all of those machines back in during the assembly line manufacturing process have to also know what the customer ordered. So imagine a machine, this machine maybe not creating this part properly, maybe customer ordered different type of motor because we have different configurations. We have stronger battery, we have configurations with a weaker battery, we have the configurations with rooftop, and all of those steps during our manufacturing process, all those machines need to be configured to match with the customer order. And there are many different variations of our R1 variants. The EDVs are built like mass-produced because they're all same configuration. But our R1 generation cars are very configurable, and all those machines need to be configured, so we have to react on that too. Now a machine needs to know, we have to be able to configure, so it has to talk with our SAP system. It has to talk to our backend systems, all the machines, to know what the customers order and whether to put a rooftop or to put the roof without a rooftop, to create a vehicle without that panorama roof, etc. Not a rooftop, a panorama roof. And of course, the end goal is load the vehicle on a rail car and ship it to the nearest location where a customer ordered the vehicle. For example, if you ordered a vehicle in DC, in Washington, DC, you cannot load it into a rail car that goes to, I don't know, on the West Coast, for example, because then you create a mistake, you have to bring it back, and you have to ship it to the right spot. So we have a software that controls that too. And we're not, even though we're not going to cover that, now you see how one small misconfiguration in every of the machines, in every of the step of manufacturing can create larger problems down the line if you even ship the wrong configuration to a customer, and then you have to either have to rebuild the car, etc., etc., etc. Now we go to, imagine everything went well. We delivered the car, we delivered the vehicle. Now we have to start collecting the information. As I said, if we go back to our pillars, the manufacturing process is done as soon as we deliver the car to our end customer. And now we have to start collecting the information. Now I'm going to briefly just try to trigger your thoughts and try to make you approach us down there at the booth, because this is oversimplifying what we actually do. And there are many apps, and a lot of software is actually behind. I need this slide actually to talk. I can't have it blank. So the factory, as I mentioned, the factory and a vehicle start sending data to, here we go. Now that the vehicle, I mean, this process, the factory process, is where the machines and the assembly line, all the machines in the factory, that's happening at all times. But the car starts sending the data from the point when we deliver it to the customer. And now we can actually learn and start investigating whether our machines have been configured properly. What I mean by that is, and I'm just going to show you how the communication goes from a vehicle to cloud and which pillars we use, thank you, which are kind of some major groups of services and how the data flows inside of our cloud infrastructure. So of course, this is not covering, by the way, a lot of things. This is not covering how the secure connection is made between the factory or the vehicle to the cloud. This is not covering a bunch of stuff. How the vehicle, from different ECUs, we collect the data and ship it like in bulk, like a stream of data. Now, the machine that created that chassis part, we can start listening to the sensors and figure out whether we made a mistake and whether we can reconfigure it differently, maybe to manufacture cars differently, all those machines in the factory. So, the first line of defense, of course, is our ingestion layer. The ingestion layer is there like it's a short-lived persistency layer. Imagine it like a queue. So, in case everything else breaks, like it broke a week ago when AWS was down, when the whole US East was down. I mean, it didn't break for us. We have failover states, of course. But I'm talking in case of an outage. In case of an outage, sorry about this. In case of an outage, our ingestion layer needs to be very resilient and needs to store the data for later reprocessing. So in there, as you can see, you have a lot of familiar faces for you that are in AWS and in Kafka, perhaps. So in front of this layer also includes, like the first line of defense are like small adapters where we just do very simple ETLs because we communicate with a bunch of different devices, factory and vehicles. And we have different, even though the customer sees it only as R1Ss and R1Ts, we know that there are different multiple smaller versions depending on the software update, which you're going to see afterwards. Not all vehicles run the same software, of course. You know, some of the customer maybe can never give consent to push a software update to his vehicle. Like probably some of you don't ever update your phone. You know, phone is forever gonna say, hey, there's a new update. No, I don't want to do it. No, I don't want to do it. I don't give consent. Likewise, our vehicles have different versions. All of our fleet have different versions of software, and they all communicate slightly differently with our cloud. Maybe we changed something. Maybe we optimized. So the first line of defense is that ETL, a very simple, like very ephemeral layer that just converts the data into a unified interface that we can put in our different queues or different streaming services that we can later listen or push or stream to different services. Okay? Approach, as I said downstairs, this is oversimplifying it by 1,000 times. Approach us down there and you're going to hear more details about it. Probably you have different questions because this is a huge part of, these are essentially IoT devices. You can look at them that way. So how do we handle our fleet of IoT devices? As I said, computers on wheels. Then after this, wow, time flies. After this, we have our data lake. This is like long-lived persistency layer. So even if, and in the last layer, the storage layer, this is where our apps read the data from. The apps that we built for the factory or for the cars. So the middle layer is actually our learning piece of the three pillars that you looked at the beginning. So here we have long-running jobs that in SageMaker, for example, or in Redshift, that we figure out how the vehicle behaves, that not necessarily you need a UI for. So we process the data very heavily, and this is where our ML models are being created. ML, why does an automotive, Rivian is an automotive industry, car manufacturer needs ML models? Well, for example, if you want to improve your car over time, you need to give the customer something. And Rivian is very famous for fix it yourself if you can. You know, it's a robust vehicle. So, for example, one of the usages of SageMaker is in our mobile app, when something breaks in a car and a customer opens the mobile app, there is an agent. And you can ask, hey, my window is not opening, the driver's side window. And the AI is going to tell you, you can either fix it yourself, unscrew these 3 screws and replace maybe something, or here's the nearest service center. And all of that knowledge, as you can see, we are collecting the knowledge even from service centers, not just factory and vehicles. Also from our service centers throughout the US, we collect information same way, same pattern applies. So first in the ingestion layer, then we learn and process the data, and then we make the data available in our apps. What I mean by in our apps, that the people in the factory see, that we see for yard management, for managing the yard, etc. All of our apps that we've built. And of course, some of the data is even available to a customer. Like, for example, the average power consumption if you're towing a 1-ton trailer. I don't know. Maybe that can be improved over time, and we're not going to use vehicle to calculate that. But instead, we're going to send the power consumption from all the 4 motors, analyze it, and tell the customer, hey, maybe you should, I don't know, get a different towing hook if you want to improve your efficiency. And of course, the last layer is where our apps read the data from. Ask us also about this layer, because we have a bunch of apps that are reading the data from this layer. The 3 databases, here are just as an example, not as an example, we of course use them, but we use all of the different, we even use graph databases, of course, relational, non-relational document database, we use a bunch of databases, different databases, because as I said, in essence, we are, even though we are an automotive company, we are a software-driven company, very software-driven company. We built like 95% of software ourselves. Even for the machines, as you can see, we're not just picking it from the manufacturer and using it how it should be used. We also try to improve it and tell it to be configured differently. Okay, let's go next. Now we are in the learning step of our pillars. Now we can go to learning, and now we need to optimize both the factory and the vehicles themselves. One of the examples how we optimize the vehicle itself, as I said, maybe we want to push a new software update, and how do we now manage a fleet of vehicles, our IoT devices in essence. So as you have on your phone, same thing applies. We push a software update on a car. And this is a bit more robust than, and a bit more scarier than updating a phone. Why? Because you cannot just update. This is, by the way, how it looks from the driver's perspective. If a new software update is pushed, you have to give consent, then it starts updating. But there are more guardrails other than, hey, tell us just whether you like on your phone when your software update is pushed. Do you want to update? Yes. So there are a bunch more guardrails in the software, and the software inside of the vehicles, all those small ECUs, send the data to make sure that even the customer gave consent. You cannot start an update if a car is moving. You cannot start an update if a car is in that pet mode, for example, where because the AC might go down, might turn off, might turn on. You cannot start a car, start a software update if there's a kid in the car. You cannot start with the windows rolled down because the software update lasts for some time. Even if customer gave consent or didn't, you have to know that we manage, and this is, we need to optimize, of course. We need to push software updates to our cars to prolong its lifespan of the parts, maybe to improve, release something, because in today's world, people expect you to update anything that you buy. You now even have smart washing machines or microwaves or whatnot. People expect you to update their thing that they bought over time. Of course, nothing ever goes well, and a software update, as I said before, vehicles can be on a different software, all of our fleet, and a software update might be queued, downloading, waiting, if a customer didn't give consent, failed, succeeded, all the different states, and you have to manage all of that. That's our adapter layer, that layer that I talked before. This adapter layer that does the ETL process, that just transforms from one version to the other, has to know all these different variations, and we can slowly deprecate the old adapters that were doing the ETLs for some old versions of a car, maybe listening to average speed, maybe the payload changed the interface over time, maybe we improved it. So this is where our ETL layer is very important, because it has to know, even for the machines at the factory, if a manufacturer pushes a software update to update this machine, we have to now build another adapter layer, because we might have tens of these machines in the factory. So we now have to build additional adapter for the new, maybe the API changed, it's something like that. So that's why I say this layer, the ingestion layer, is very important. Even though it's short-lived persistence, like a couple of weeks of persistence, it's very important because without it, everything else doesn't make sense. And for you to consolidate the data in these two pillars, you have to have a stable ETL process and a stable initial processing into events. Because if you just forward events, all kinds of events, whatever the origin is, and no matter how they come in which format, if you just forward it, you're going to create a mess downstream for us, for engineers, for developers in our apps. Because now each of the teams have to process all the different versions of events. If you streamline the interface for these two pillars and you just do ETL once, then all the teams know what the interface is from a device they're talking to. They receive the data from, sorry. Okay. So, we're running out of time. I have much more to say, but let's slowly start wrapping up. Even though the slide says architecture, this, like, maybe a more better wording would be a direction. So you saw how one signal from one machine from the factory can affect the vehicle, can affect future vehicles, can affect our cloud, can affect how we develop apps for the company, and then bring it all back. You have to bring it all back. This is a very nice architecture to have if you're developing any kind of tool. If you have a factory for anything, it's nice to have that end-to-end reactive architecture where you can listen to events even from while you're manufacturing stuff, then all through its life cycle, and then improve either the manufacturing process or the existing your selling point, whatever you're selling, whatever that thing is that you're manufacturing. In this case, it's cars, it's R1Ts, okay? So that's why even if your architecture, if you're developing chips, for example, even if your architecture is not reactive end-to-end, from the manufacturing process to usage process to then cloud process and then back to the manufacturing and the existing devices that you've sold. Even if it's not implemented, even though it's not reactive. For example, you only use machines as a black box, how the manufacturer said the bolt had to be tightened this way and that's the only way and that's it. Okay, bolt maybe is oversimplifying, but you know what I'm saying. Even if you don't use it, it's very easy to slowly transition to. So you can start building a software. You can ask the manufacturer for APIs, for configuration patterns, for interfaces, and you can slowly start converting one by one of your manufacturing process into a reactive kind of architecture where it can react later down the line. When the analysis is done, you can push a new config to your machines or to existing devices, new software update that might improve it, might prolong the battery life. I mean, that's the core value of it. If you have end-to-end reactive architecture, the only thing you're essentially doing is, first of all, you're going to simplify manufacturing process like we did, going down from almost 30 ECUs down to 14 ECUs. You simplify your manufacturing process and you improve the quality of the existing devices over time. And of course, being data-driven, as Rivian is heavily data-driven, as you've seen, that middle pillar where we analyze the data is very important for us because that data can be reused for future generations of a car, like we have already announced for next year. Well, since we have 2 more minutes left, I'd like to go through if we have any questions for this topic. And I urge you again, if you have any questions, what do we do in the Belgrade office? Because we do firmware development for ECUs. We do the factory software development where you saw that UI where it says which bolt is tightened to which extent. We do backend, we do infotainment. This infotainment in our car, all the displays, all that software is being built by us. And as I said, like 90%, even more than 90% of the software that our car runs onto has been built by us. So if you have any questions, please do ask. Otherwise, approach us. We're downstairs at the booth. It's literally engineers at the booth. So ask us what do we do and how do we do it.
We have one question here. Please just, let's wait for the mic because we have online people watching from online.
Is it turned on? Okay. So a quick question. You talked about data-driven optimization of the processes and detecting if there's a rattle in the car, for example, if that was your example. Have you ever had like a recall based on what you found from the data? Oh, we found in this car, we need to kind of change this bolt for a different bolt, like plastic to metal. I don't know. You get my question. Thank you.
Thanks for the question, first of all. Of course, whatever you're manufacturing, you might end up having a recall. Luckily, Rivian never had a recall in its entire life cycle of its vehicles. But a software update can fail. It can happen. Different situations. A battery might be too cold, so it ran out too fast. Sensor was bad, and the reading was bad because we might have detected that there is enough battery. Okay, I'm over-exaggerating. This is not going to happen. We might have detected, we might had a wrong reading from a sensor. And based on that, based on our guardrails, we thought it's safe to start the software update. It might not have been safe to start the software update. But we learned from all of our mistakes, and for a very long time, all of our ECUs actually have a rollback mechanism. So we do blue-green deployments now in all of our ECUs. So even if a software update, even though in our UI it can say it failed, a car is going to roll back to a previous software. But we know that something failed, and now we have to investigate, look at the logs, because when the software updates, you mentioned the rattle. Yeah, those hardware recalls, we never had them. But software, it can happen that it could have happened. Now it can. I can't recall that it happened during. I never heard that it happened from somebody in the company. But I know that a long time ago, our firmware team developed the blue-green deployments for all of the ECUs in the vehicle.
Nice, thank you.
Thank you, Nemanja. Unfortunately, we ran out of time.
I know.
Yeah.
Sorry.
But thanks for the presentation. If you have any questions, you can approach the Rivian booth, Nemanja directly, and ask them there. So thank you, folks. We'll see you back here at 10:50.